And we are live.
Okay, hello everyone. I'm John Iacono. I'm your session chair. I'm at the Free University of Brussels and New York University. This is session C3 of ICALP. We're going to have 6 talks in this session. And what I'm going to ask is that each presenter start by giving a short, approximately 2-minute quick overview of their result. It's hoped that everyone has seen the videos already, so this is just to refresh everyone's memory as to who you are and what your result was. And then afterwards, we'll open the floor to questions. You can either type the questions on Slack, on Zoom, or if there's a reasonable number of participants and it seems to work smoothly, you can just sort of ask them directly. Right now, we're only 16 people, so that will probably work best. So without further ado, the first talk is Active Learning a Convex Body in Low Dimensions by Sariel Harpaled and Mitchell Jones from UIUC and Salati Raul from IIT Bangalore, and Mitchell is giving the talk.
Thank you. So I'll just go ahead and share my screen. Okay. Oops. Okay, great. Yeah, so let me just refresh everyone on the problem that we talk about in this paper. So you have a collection of points in R to the D. Again, think of these in low dimensions, like D equals 2 or 3. And you have a convex body. And how am I giving you this convex body? I'm giving it to you via access to what we call a separation oracle. So the separation oracle is, you can kind of query this oracle for any point in R to the D. And the oracle either tell you that it does indeed lie inside the convex body, or if the query point lies outside the convex body, it gives you a separating line, or in higher dimensions, it gives you a separating hyperplane as proof that the query lies outside the body. So if we only have access to the convex body via the separation oracle, what we would like to compute is for every point P, in my point set, whether or not it lies inside or outside the convex body. So essentially, I just want to classify these points as being either inside or outside. And here we're interested in not necessarily the running time, but just the fewest number of oracle queries needed. And it turns out that in our paper, we get algorithms in which the number of oracle queries depend on the structure of the input instance. So we're looking for algorithms which are instance sensitive in terms of the number of queries. So these are just some of the results I've highlighted here. So the main one which I mentioned in the talk was this first one, classify in 2 dimensions, where we show that there is an algorithm where the number of queries made is kp log n, where k of p is the largest number of points in convex position. We also derive a lower bound on the number of queries that any algorithm has to make, and this lower bound is something known as the separation price, sigma pc, which I can go into more details, but it's discussed in the talk. And then in 2 dimensions also, we were able to get an improvement, so an improved algorithm which runs in sigma pc log squared n times. So this is essentially matches the lower bound up to a polylog n factor. In 3 dimensions, we were able to extend the first algorithm, which uses kp log n queries, into 3D to also get kp log n queries. But this is the best result we have in 3D. And we didn't have any results in 4 dimensions or higher, and that's completely open. So these are essentially the 3 results. That's probably the end of my highlights. So I guess I'll jump into questions if people have any.
Thank you. Open the floor to questions. Feel free to just speak if you have one. I'll ask that this somehow seems like in the same vein of work as the paper by Payman and Timothy Chan on this instance-based optimality a few years ago, which they used to compute convex hulls and stuff like that. Is this sort of, what would be the next thing to look at in this sort of line of project of trying to make things instance-based optimal in terms of the number of things for that particular instance?
I'm not sure, actually, I'm familiar with the exact paper you're talking about. In terms of next line of work, I think for this particular paper, I think the natural line is to consider either obviously other models rather than just using separation oracles. But we'd also thought about looking or working with non-convex sets, right? So maybe, So if the object is non-convex, maybe, but you're assuming it's sufficiently smooth. One possible model we had considered was thinking about with a query, you're given a query point and it returns the distance from the query point to the boundary of the body, for example. This is equivalent to saying returning the largest disk centered at the query point contained inside the body. So I think from this particular work, I think we can consider other models and other objects. I think also coming from this line of work, I think higher dimensions would be more interesting, right? Obviously, we're motivating this from a machine learning perspective, and in practice, you're not working in 2 or 3 dimensions. So I think really we want to get some sort of high dimensional type results. But I think this seems like actually a very, very hard problem. And, we thought about extending this to higher dimensions, but the number of queries you end up making is very, very large. And at that point, you may as well just query every point individually, which is just a brute force. So going from this line of work, I think it's really getting the high dimensional generalization.
Okay, any other questions?
If I may, so you are saying that for high dimension, it's more complicated. What would you expect in high dimension? What would be your target?
Well, okay. So this lower bound we have on the separation press, we can certainly extend to higher dimensions. Just the definition. So, getting something that matches the lower bound up to, say some polylog factor would be nice. So this algorithm, this greedy algorithm, which is this first result, you can extend. Actually, I believe you can extend this to high dimensions. I haven't gone through and done the analysis, but the number of queries is really going to be something like k, probably to the O of d log n or something like that, right? Which is already pretty bad, because if k to the d is much more than n, then forget it, right?
Okay.
So.
But what is the best case scenario? What would you hope?
I mean, I guess the hope would be to match the lower bound, right? But I don't think that's. I think this just seems like a very hard problem. The analysis is even in 2D is very non-trivial.
Okay. Okay.
Yeah. I mean, anything really, because we don't have any results. So I find it hard to. Anything would be nice than. But I mean, I guess you would expect some exponential dependency in the dimension, just because.
Yeah, that's what I thought. But then you are saying that k2 of d is too much.
Yeah, but perhaps you can hope for maybe 2 to the d or something, where the base, is not depending on some input parameter. So I mean, maybe it would be nice to get some 2 to the d times k or something like that. I don't know.
I see. Okay, thank you.
Okay, and finally, there was a question in Slack that was asked about. Can you maintain an under approximation of the convex body? Can you also do it with an over approximation? Yeah, right. So I did see this question. My answer to that is probably, and the greedy algorithm already kind of does this. So let me actually move to a blank piece of paper. So the greedy algorithm, what it's doing is you have your convex body C, right? And every time you find a query point which is outside the convex body, you get a separating line. So you get a bunch of these separating lines. And whenever we get a separating line, we can mark a lot of points as being outside. We can classify them. So in a sense, what you can think of the greedy algorithm is doing is implicitly maintaining kind of the intersection of all of these half spaces, right? And this is kind of like an outer approximation or an over approximation of the body. So the algorithm is kind of doing this implicitly. We just don't mention it in the paper. But I mean, yeah, whether you use the inner or an outer approximation, I think you'll get some similar results. Okay. Any last quick question? Okay. If not, thank you very much. And we'll switch over to the second talk of the session, which is Polytopes, lattices, and spherical codes for the nearest neighbor problem. The speaker and sole author is Thijs Laarhoven from Eindhoven.
Yeah. Okay, so let me share my screen. Does this work?
Yes.
Okay, so so the topic of my talk, my paper, is about nearest neighbor searching. So basically, the problem is, like, given some high-dimensional data set, you want to store it in a data structure such that when you're later given a query point, you can quickly find the nearest point in this data set. So, like, the most similar item in this data set. You can consider this problem for lots of different metrics, but so for this talk, for this paper, it was focused on the angular distance, or equivalently, if you have a data set which lies on a unit sphere and you want to find the nearest point under the Euclidean metric. And so past work has mostly focused on the approach like, okay, so your data set lies in very high dimensions usually, and then it's kind of hard to find similar items there. But what you usually do is you take your high dimensional data and you project it onto a lower dimensional space, like only 2, 3, or like a few dimensions, and then you partition this lower dimensional space into regions, and then you use these regions to only search like part of the space for near neighbors, like the same region that your query point is in after this, say, projection. So most work has focused on this like kind of project and partition framework, and that's also formalized in this paper, like this whole idea of projection and then partitioning. And then the main question that you have is like, how do you actually partition this this low dimensional space efficiently, like this low dimensional sphere? And basically what you want to use for that is some kind of nice spherical code, which can be like formed by some nicely shaped polytope or by some regular lattice, which has a nice shape. There are different ways to do that. And so the main topic of this paper was to figure out like which of these spherical codes are the best for partitioning low dimensional spheres into regions, so that like for this problem of nearest neighbor searching, you actually get the best results. So okay, maybe I should just okay, so just going to the contributions. So okay, so so this paper was about formalizing this framework of projection and partitioning. So that's like this theoretical framework. So actually this tells you exactly, like, given some kind of spherical code in a certain dimension, like what is the performance of this code for the nearest neighbor problem. And this actually also allowed us to solve this two-dimensional case explicitly. Like in the past, we've solved the one-dimensional case, and now we can actually show that, okay, if you want to use two-dimensional projections and partition them, then you should partition it into 3 regions formed by a triangle. And for high-dimensional projections, already it becomes too difficult to get exact expressions for the performance of such a code. So yeah, for high-dimensional codes, still you can do like numerics, like this paper does give a recipe like how you can compute the performance, but like you don't get analytic expression. You just have to compute some integrals, and you can do that numerically. And then you can still compare them, and then you can figure out that, okay, in certain dimensions, like usually like these orthoplices or the simplices are the best. So still it gives you some idea like what you should be doing. Also for comparison, like we don't really know what are the best spherical codes, like which actually exist. And so as a guideline, there's also this result on lower bounds for, like, if you project into a certain dimension, like how big should your partition roughly be, like how many regions should you use. That's based on these spherical cap estimates. And finally, at the end of the paper, there's a bit of practical consideration, like which spherical codes you actually want to use, like how you can actually efficiently compute like the regions that you're in, etc. So basically that's short outline of the paper.
Okay, thank you very much. I'll open the floor to, are there any questions? About spherical codes. Anyone? I guess one thing is to sort of make clear as to the usefulness of this are you talking about by improving these codes? Are you improving the runtime of other algorithms by constants, or are you really making large differences, observable distances in runtimes?
Yeah, so for instance, what has been used a lot in practice before is this hyperplane hashing by Sharikar from like early 2000s. Like people have been using it, but like we know that it's asymptotically suboptimal. Like you can do better like with cross-polytope hashing. Like cross-polytope hashing has a lot of hidden order terms that we still have to figure out. And like this high plane hashing is actually quite practical because it has no hidden order terms and it's actually very efficient. And so like the schemes considered here are also in the same category of being efficient, but maybe not like asymptotically optimal. Like it depends a bit on how big your problem sizes are, etc. But like there is some practical usefulness if the problem is not too big. I mean, if the problem is really big, then you probably want to use the asymptotically optimal schemes like the cross-polytope hashing, for instance. So yeah.
Okay. Any other questions? Okay. If not, then we can move on to the third talk. The third talk is on the two-dimensional knapsack problem for convex polygons. And the authors are Arturo Moreno and Andreas Weiss from TU Berlin and the University of Chile. And Arturo is giving the talk.
Yes, thanks. So let me share my screen. Okay, so does this work? Seems so. Okay, so let me quickly recap the problem. So we're given a square knapsack of side n, where n is an integer. We're also given m convex polygons, and these polygons will have some weight associated to them. And the thing is that we are allowed to translate and rotate these polygons as we see fit. And what we want to do is we want to find a subset of the polygons such that first they fit non-overlappingly into the knapsack. So let's say that we first take this polygon, we translate it into a knapsack. So currently it doesn't fit completely, but after rotating it, we can make it fit. And let's say we keep going with this one. So in here we see the two problems. So not only is not completely contained into a knapsack, but it's also overlapping another polygon. But again, after some rotation, we can make it fit completely and non-overlappingly. And what we want to do is to maximize the total weight. So this is somehow a very low solution, very low weight solution. But by keep doing this process of translating and rotating, we can achieve this weight optimality. So somehow I want to also highlight the two key novelties that we somehow introduce in this work. So the first one is that we did with convex polygons. So all previous work has only talked about axis parallel rectangles. And now we deal with arbitrary convex polygons. And the second big thing that we do is that we allow for arbitrary rotation. So previous work had only considered 90-degree rotation, but now we allow for rotation by essentially any given angle. And we have 4 results. So our first result is that we obtain a constant approximation for this problem in quasi-polynomial time. If we restrict ourselves to only having triangles as the input, we can actually improve the running time to polynomial time. And then we have 2 results in the setting of 1 plus delta resource augmentation. So this means that we take the original knapsack, we stretch it by a factor of 1 plus delta, but we compare ourselves to the optimum of the original knapsack. And in this setting, we can get a constant approximation in polynomial time. And we also have an algorithm that returns a solution of weight at least the original optimum, and it does so in quasi-polynomial time. So this is the summary.
Okay, thank you. I'll open the floor. Are there any questions on this?
Yes, I have a question. And you notice that you have rotation and translation. Does your result also allow mirroring of the polygons? Or is that something that's just not of interest?
I mean, I guess we didn't thought about mirroring actually, but now that I think of it, somehow it's very interesting because somehow when we think of this, we think as having, I don't know, so a sheet of raw material, and we have somehow some molds, and that we can cut our raw material, and of course you can take the mold and just mirror it. So yeah. I mean, we just didn't thought about it, but these results only allow for translation and rotation. But yeah, one could do something for mirroring, maybe.
Okay, there's a question that was posted on Slack. It says, I know this is mainly theoretical work, but can you say something about practically interesting instances of the problem. In particular, regarding the open questions you posed, I wonder where each of these problem classes appear in practice, or whether they're mostly interesting for theoretical reasons.
Okay, so I think mainly the main interest somehow is theoretical, but I think that this problem is very natural and very practical. So somehow I think that the basic meta somehow application is to, as I said, somehow think that you have a sheet of raw material and that you somehow want to cut this raw material into pieces. So let's, I don't know, be more concrete and think that you are, I don't know, IKEA, and you have somehow a big slab of wood and you have to make your tiny furniture pieces, and then you have to cut the wood. And if you do it really naive and really badly, then you lose a ton of wood and you're somehow happy. And somehow this is also dependent on, so your profit is also dependent on the shapes, or I don't know, so somehow you can keep replacing this framework and think about that you have a piece of metal and then you want to cut the metal, or I don't know, you have cookie dough and you want to make cookies with some cookie cutters. So I think somehow the basic framework is about raw material and cutting the raw material up. And about the open questions, so let me quickly shift to this. So I posed 3 open problems at the end. So the first one is about small polygons. So I think that this is somehow like in a practical setting, the interest is that while you are doing somehow all of your small items at once. But I think that this is somehow very interesting because our work implies a 7 approximation for this. So this is somehow a very good starting point to get a reasonable approximation in a somehow interesting context about weights given by area. So this also I think is very, very natural. So this is basically saying that the profit given by your object is basically given by the raw material. So somehow it's saying that the shape doesn't matter. So let's go again back to the setting of the cookies. So this is saying somehow that the only thing that matters to you about the cookie is the weight and not really the shape that it has. So you're not really fond of, I don't know, octagons or squares. You like them all equally. The only thing that matters to you is eating somehow as much cookie as possible. And this can be translated to those settings. And the one about arbitrary polygons, I think that this is also very natural. Like, I don't know, if you want to eat cookies that are non-convex, for example, I don't know, stars or a Christmas tree or something. Yeah, very natural.
Yeah, I can imagine too, given today's obsession with COVID, that if you had a polygon representing the area where you can't have another person, you want to know how many people you can pack in a room where there'd be a selected dot in the polygon. And the idea is you don't want to touch those. You could have, there's a lot of different room for all sorts of variants here. Any other questions?
There is a question
About,
in the chat.
It says, wouldn't mirroring just increase the input size by a factor of 2?
I mean, but somehow you're also allowing to use the polygon twice or not? Like if you take the polygon and also allow the copy, then you can somehow pack both of them into the knapsack. But if you only allow for mirroring, then you can either get the original polygon or the mirror copy. Or not.
Yeah.
So I will have to think about it if maybe some reduction is somehow simple, but I don't see it somehow so clearly.
Okay, and there's another question that's been asked of, do you know of special cases where you can solve the problem exactly in polynomial time? I'm thinking about a reduction to the existential theory of the reals. Constant number of simple pieces implies polytime.
This is actually a very good question. I would guess so is if somehow you have a bounded number of edges, or you could start thinking about something like this. Because yes, you can somehow, yeah. I mean, constant work, maybe logarithmically many. I will have to think about it, but yes, in principle, you can somehow write this problem as in this existential theory of the real setting and somehow use that this is contained in P space and somehow try to do something like this. So I guess if you have very, very few edges, something like this could work. Very good question. I will have to think about it, yeah.
Can I just say that, well, what I meant was if you've got kind of fixed number of variables, then that fragment of the theory is decidable in polynomial time. So if you only have like constant number of polygons with at most like 10 sides, then you would have kind of a theoretically polytime procedure, even though it can kind of really take loads of time in reality.
Yes, that is, I think something like this definitely will work. Like,
Thank you.
yeah.
Okay, are there any other questions? Okay, if not, thank you very much. And we'll go on to the next talk, which is near optimal algorithm for constructing greedy consensus tree by Hongshun Wu from IIT at Tsinghua. Okay, we can't hear you. Hongshun? There's no audio right now. Hongshun, your audio is muted.
I'm sorry, is this fine?
Yes, now it's working.
Now?
Yes.
Okay, this is where I'm sharing. Okay, I'm sharing screen from my laptop and having voice from my PC. So.
Okay, that's fine. We can hear you fine now.
So this problem is about constructing greedy consensus tree in near optimal time. The input of our problem is k phylogenetic trees, each with n leaves in it. Okay. Each with n leaves in the phylogenetic tree. Each leaf of the phylogenetic tree represents a species, and since the input trees may conflict with each other, we need a consensus tree to summarize their structure.
Your audio is gone again. The audio is still not there. The audio is showing as being muted. Function? There's still no audio.
I think he left and he's trying to log in again.
Yeah, I see him twice here.
Yes.
On the screen, but.
What happened? It seems that I just lost connection.
Okay, you're back now.
Okay, I'm sorry for that.
Okay.
So does the share screen work, or
No, we don't see it anymore.
or only the voice?
Oh, only the voice.
Okay, maybe I should start again.
Yes, please.
Thanks. Because okay. Is screen sharing working now?
Yeah, everything's working fine.
Okay, that's good. So so this is Hongxun, and our paper is about near optimal algorithm for constructing greedy consensus tree. So so our problem is like following. The input are k phylogenetic trees, each with n leaves in it. The leaves of the tree represent the species, and a phylogenetic tree represents the evolutionary relation between the species. The output is a single phylogenetic tree, which serves as the consensus of these k phylogenetic trees in the input, because these k phylogenetic trees may conflict with each other. And we need to take, like, if you have some conflicting numbers, we will take the mean of them. And here we take the consensus tree as the estimator. The greedy consensus tree basically prioritizes the structure which occurs more often in the input trees. It sorts the structure according to their frequency in the input trees and add them to the consensus tree one by one. And if a structure conflicts with a previously added structure, then we just abandon the structure. So the input size of our algorithm is kn, since there are k phylogenetic trees in the input, and each of them has n leaves. So our result is about how we can construct such greedy consensus tree in near optimal time, which is OTL at kn time. It is optimal up to polylogarithmic factors. Since our algorithm is actually a very practical algorithm, we will upload an implementation to GitHub because it might be of interest for some like bioinformatics purpose. Thank you. This is end of my talk.
Okay, thank you very much. I'll open the floor. Are there any questions?
Yes, indeed. I have a question. So from your motivation, it seems like this is basically for these phylogenetic trees of species. But I wonder, does it necessarily have to be that every tree has to contain every species? Because I feel like in nature you would have people would have some subpart of the tree only and don't include all the species necessarily. Would your algorithm also work somehow with those kind of trees as well?
You're muted. We don't hear you.
Oh,
there you are.
Sorry, I think the connection is bad. Can you please repeat the question?
So yes, so far you have k phylogenetic trees with n leaves each. What about if some tree doesn't contain necessarily
I think
all
the internet connection is...
Maybe you can type the question.
I'm going to type the question.
Yeah. Thank you. Yeah.
I'm sorry. I think the internet connect just broke again. Can you repeat the question? Or
He's going to type the question.
Okay, I see. Thank you. Just broke again. Can you repeat the? Okay, I see. Thank you.
Okay, the question is there in the chat on Zoom.
Oh, I see. I think the algorithm may break down at some point because we heavily rely on the tree structure. But that would be an interesting problem to look into, I guess.
Okay, are there any other questions? If so, please shout and type it.
Again, I'm so sorry for my terrible internet connection.
No, it's okay. It's our fault because we should be there with you, actually, in China right now. Okay. May I ask, can you say just simply what is the magic that makes this work? Because this is a well-studied problem and this is a huge improvement over the previous results. Is there some easy way you can describe what's the one thing you saw that no one else saw?
Yeah, it's actually a very simple idea. The previous algorithm basically use a calculation of consistency, which requires you to find the least common ancestor of a subset on a dynamic tree. And basically, they have many fixed subsets, and then to dynamically maintain their least common ancestor on a dynamic tree. And basically, that's very hard. So I take another approach, and I used another calculation, which requires you to find the least common ancestor of a subtree in the dynamic tree on those k input static trees. And that is very easy. That's basically why we can improve upon previous algorithm.
Okay, thank you very much. Are there any other questions? Okay, well, thank you. We'll move on to the next speaker. The next talk is Computational Complexity of the Alpha Ham Sandwich Problem. It's by Man-Kwon Chiu, Runi Chaudhry, and Wolfgang Molzer, all three from FU Berlin. And Runi is giving the talk.
Hi, so do you see my slides?
Yes, we do.
Okay. So the problem that we looked at is the alpha Ham sandwich theorem. So this is not really about sandwiches, but about point sets in Euclidean space. So there's a classical theorem called the Ham sandwich theorem, which says that if you have d point sets in d-dimensional Euclidean space, there's always a hyperplane that essentially bisects all of them at once. And the alpha version of this is motivated by thinking that what if we want not half, but some other ratio? What if we want some alpha I ratio from the point set Pi? So for example, here we have 2 point sets in the plane. And if I want 7 blue points and 4 orange points, this is the line. This is an oriented line, and this half space contains exactly that many points. So the computational version would be to find such a hyperplane. And this does not always exist. There are some certain conditions that the points must satisfy for this hyperplane to exist. And the problem here is to find this hyperplane. So there are algorithms to do that, but they take exponential time in the dimension. So what we try to do is to place this problem into a complexity class. And this complexity class looks something like this. So this is a bit of an eyesore, but so here you see many complexity classes which are related to finding search problems. And so for example, this class PPA, this is related to problems which can be solved using Borsuk-Ulam theorem. And CLS and PLS are related to local search problems. And last year, a new class was introduced, which is called unique end of potential line. And we showed that this computational problem lies in this complexity class. So for the regular Ham sandwich problem, where you just want a bisection for each point set, that lies in this supposedly larger class. And that is also complete for this class. This was shown last year. But we do not know any hardness results for this problem yet. So if you have any questions, I'd be happy to answer them. And if you want to read a longer version of the paper, you can go to this link.
Okay, thank you very much. Are there any questions?
So maybe I will ask a question. So I do know the end of line problem from game theory.
Yeah.
Unique end of line problem, potential line is a related problem. How come did you find a connection between these problems?
So it is. So it's a bit random. So the intuition for showing that this problem is in this class is quite simple. It's like you take a hyperplane that is basically tangential to all the point sets, and then using some local changes, you can rotate the hyperplane until you reach the fixed solution. And the solution is always unique if there are some conditions on the point sets are satisfied. And then we saw, then we looked at this problem, which modeled problems which had unique solutions. And then we saw that it's not really difficult to follow it. But yeah, the details of how we handle some cases when these conditions on the input point sets are not there are a bit complicated.
Okay,
but
okay, go on.
But the basic intuition is simple.
Okay, but then, so of course, game theory, I mean, Nash equilibria, etc. These are claims about some geometric objects, but this is somehow a different type of geometric object. Does it give any hope that one could say more about these complexity classes?
So there are also some other geometric problems here, like finding the fixed point for a contraction map and things like that.
Okay.
And then there's a unique sink orientation problem. So that is also a bit geometric. Right?
Okay, good, thank you.
Are there any other questions? I can ask, does this work with separating planes instead of planes separating polynomial surfaces of bounded degrees?
Could you repeat the question?
For the ham sandwich, instead of, can you work with different sorts of separators? Like in the classic ham sandwich problem, you can also have different number of things you separate if instead of using line, if you use higher degree curves.
Yeah, if you use polynomials. Yeah, I haven't thought about that. So the complexity of that, yeah, I don't really know at this moment.
Okay. Any other questions? Okay. If there's no more questions, then we'll move on to the next talk. Thank you very much. The next talk is Succinct Filters for Sets of Unknown Sizes. The authors are Mingmu Liu, Yingtang Yin, and Huasheng Yu, who are from Nanjing, China, and from Princeton University. And Mingmu Liu is giving the talk.
Hi, can you see my screen?
It says it started, but I don't see it yet. Ah, there it is. It's there, and I see you fine.
Okay. I'm going to present succinct filters for sets of unknown sizes. This is a joint work with Ying Yitong and Yu Huachen. Filter is one of the most popular approximate versions of the dictionary problem. The problem asks for a data structure, supposing first, insert a new element, second, check if an element has been inserted, and a small false positive rate is allowed. In this work, we present a succinct data structure. A data structure is called succinct data structure if the space cost is very close to the minimum space to store the database. In the setting of unknown sizes, the final size of the database isn't known in advance, so the space cost of the data structure has to depend only on the current database size over its lifetime. In practice, we usually don't know the final size of the database. On the other hand, constant worst-case time is highly demanded in many applications. In TCS community, Pei, Sigib, and Weider were the first to study this problem. In their seminal work, they proved a lower bound for the filters and provided two data structures. PSW left an open problem. They asked that if there is a space and time efficient
we lost your audio.
enjoys.
We're back. Okay, sorry, continue.
Okay. In this work, we present such a data structure that simultaneously enjoys the best of both worlds. In fact, the space complexity is even better than what PSW expected. In this work, we provide data structures for filters and dictionaries. Both of them are succinct and has constant worst-case operation time. In this talk, we focus on the succinct filters. Now, the technique overview. We solve the filters by reducing it to a problem named prefix matching. With a simple observation, our reduction introduces at most O(n) log U bits of redundancy. To solve the prefix matching problem, we present a succinct membership data structure. It turns out that our data structure solves the reduced prefix matching. After order reduction, we apply the standard double when-full method to reduce it to a succinct data structure with capacity. Our membership data structure adapts the idea of sub-data structure. We randomly place n data points into n over log n sub-data structures. Then, every sub-data structure receives O log n data points with high probability. We dynamically resize the capacity of every sub-data structure so that there is no overflowing data points. The critical component is how we access the data points in sub-data structures. Previous solutions randomly store the data points and equipped every data point with a pointer to access it. The pointer uses log n bits because there are log n over log n data points in any sub-data structure. In order to reduce the space usage, we develop an idea of data block. One may consider the data block as our main technical contribution. We get the data points into log n groups. Every group is stored orderly. We name the tiny structure data block. At data point, all we need is the index of the data block together with some in-block information. To summarize, we spend at most extra log n bits on every data point. In conclusion, we presented the first succinct filter for sets of unknown sizes. Our data structure enjoys the best of both worlds. The data structure has constant worst-case operation time and is space efficient. The key idea is data block. Our data structure solves the problem by reducing it to prefix matching. There are some interesting open problems. It is easy to see that our data structure is not space efficient if epsilon is constant. So can we close the gap in this regime? To the best of our knowledge, there is no lower bound for dictionary problem for now. So it is interesting to close the gap for dictionary too. That's all. Thanks for your attention.
Okay, thank you very much. Are there any questions? I can ask this. You've done an excellent job here of really closing the gap on this fundamental problem. What would be the next succinct problem in data structures that you think we should look at and where there's a gap that could be closed?
The dynamic dictionary problem, I think. Mm-hmm.
Okay, are there any other questions for the speaker? Okay, I don't see any, so I'd like to close this session and thank all of the speakers. You have about a 40-minute break now for coffee, cookies, or whatever you want until the next session begins in about 41 minutes, wherever you are. Okay, thanks again, everyone.
Thank you.